Welcome everyone. In this lecture, we're going to have a quick crash course in NumPy arrays. When we actually read in image data, the computer is going to read it in as an array. In the next lecture, we'll describe that relationship between images and arrays in further detail. For right now, let's go ahead and focus on just pure NumPy, how to create arrays, and a few operations indexing and slicing on arrays. I'm going to head over to Jupyter Lab now. Okay, here I am at Jupyter Lab. I'm going to go ahead and open a launcher, so that's the plus button in case you don't have it yet, and then click on Notebook here. And now I have my Jupyter Notebook. Let me collapse that file, and I can also close the launcher. So the first thing we need to do is actually import NumPy. And the way we do this is we say import NumPy as NP. And I'm going to zoom in just a little more so you get a nice clear view of that. Okay, NumPy has already been installed as part of your environment, so you should already have it. There's a couple of ways we can create arrays. Most often, we'll just be reading images, and that will automatically create the array for us. But in case you're interested, for a couple of other ways, if you have a normal Python list, such as my list is equal to 1, 2, 3, if you wanted to, check the type of my list here. It'll report back that it's a list. But what we could do is cast it as an array by saying np.array, and then passing in my list here. And you'll notice if I just have it be returned, it returns back an array object. So then I could say something like my array is equal to np.array, and then I have my array here. And I can also check the type of my array, and it will report back, yes, in fact, this is no longer just a normal Python list, it's actually a NumPy array. So what's nice about these NumPy arrays is they're going to be able to take in different dimensions, so I can have a two-dimensional array. So let's show you a couple of ways to create arrays that are more than just a single list being casted to an array. One method I could use is the arrange method. And np-arrange, what it does is if you do Shift-Tab here, it'll give you the documentation string. Basically, it returns evenly spaced values within a given interval. So you give it a start and a stop and an optional step size. So here I could say start at 0 and then go up to, but not including 10, so 10 is the stopping point, and then give it a step size. Well, we'll go ahead and say 0 through 10 first. So here's my array, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Essentially, this is the range version in NumPy. So as you may know, Python has a built-in range function. Arrange is NumPy's version of that. So it goes up to, but not including 10, so 10 was its stopping point. As a third argument, you can pass in a step size. So by default, it's just taking a step size of one integer or plus 1 at a time. If we say 2 here, then it'll take a step size of 2. So it'll go 0 to 2 to 4 to 6 to 8 and so on. Okay, now often what we're going to be doing is creating a two-dimensional or three-dimensional array, all of one single value. So np.zeros is a useful function we're going to be using quite often. np-zeros, the main argument you do is just the shape. So what shape do you want this array? And what we're going to do here is say shape is equal to, and then you pass in a tuple. So I'm going to say I want a 5 by 5 array. And here we have 5 rows by 5 columns. So just to make that clearer, I'm going to say give me a 10 by 5 array. And you notice now I have 10 rows. So this first dimension, the index position here at 0, that's going to be the actual number of rows, and then the number of columns is the second one. So here we have 5 columns. Now you'll notice each of these zeros has a little decimal point after it. That's because by default, NumPy is going to automatically create floats instead of just pure integers. So arrange created integers, np-zeros is going to create floats. So it's 0 point instead of just 0. So if we check the type of 0 by itself, that's an integer. If you check the type of 0.0, that's a float. And then if you just check the type of 0 point, that's also a float. So keep that in mind. These are all floating point numbers. So zeros is something we're going to be using often throughout the course. The other one we're going to be using often is np-ones. And it's going to be the same thing. It takes in a shape argument. So you say shape is equal to, and you can say 2 by 4 or whatever shape you desire. And then we see 1 point for 2 rows by these 4 columns. Keep in mind, you don't have to declare the shape parameter. Often you'll just see it done like this, and that's the same thing. All right, so that concludes talking about how to create arrays from scratch. The main ones we really need to know here that we're going to see all the time throughout the course is np.zeros, which creates an array of zeros for us, and np.ones, which creates an array of ones for us, where this first value in the shape is how many rows you have, or the height of the array, and the second one is how many columns you have, or the width of the array. So a little bit counterintuitive as far as relating the first one, number of rows to height, and the second one, number of columns to width, but that's going to make a lot more sense when we start reading in images. Okay, now let's go over a couple of operations. I'm going to do Shift Enter a couple times here to get some new cells to kind of clear some of that old stuff out of the way. So now what we're going to do is we're going to start off by setting what's known as a seed. So we're going to say np random seed and then pass in 101. What this does is it allows me to create the same random numbers each time. So I'm doing this because I want to have some random numbers for this next series of operations. So if I wanted to create random data, I just need to say np.random.rand, int. And if you do Shift Tab here, basically this describes this particular function. It's just going to create and return random integers from low inclusively to high exclusively. So that means I'm going to say here, grab me from 0 to 100, give me 10 random numbers. Notice how my seed and the creation of this array are actually happening in the same cell. The reason I have 101 here is just a seed number. The actual value is pretty arbitrary, but I want you to use the same number I do. That way, when you actually create these random values, you get the same random numbers I do. And you can do a Google search on things like random generation or random number generation to actually figure out the complex mathematics behind these seeds. But for our purposes, that's kind of irrelevant to the course. I just want to make sure you get the same random numbers I do. So if you run this in the same cell, when you get that array, you should now get the same values here, 95, 11, 81. And what we're going to do is immediately after that, create one more array. So we'll say np random rand int and say grabbing numbers from 0 to 100, give me 10 more numbers. And then you check out that second array value, you should get the same values I do. If you do not get the same values I do, go ahead and just rerun these cells again in the same order. Okay, so now what we're going to do is show you a couple of operations that are useful, such as finding the max and min and mean of an array. So if you ever want to find out the max value of an array, you can say arr.max, and this returns back the actual max value. So notice here the max value is 95. If I wanted to figure out the location of that max value, I simply need to say argmax, and it'll return back the index location of that value. So at index 0, just like a Python list, you'll notice here that we have 95. Okay, so we can do the same thing for min. So I can figure out the minimum value by saying r.min. So the lowest or minimum value in this array was 9. And if I wanted to figure out its location, then I just say argmin, and it's at index location 7. So if I count over starting at 0, 0, 1, 2, 3, 4, 5, 6, and then at 7, we have the minimum value of 9. Okay, and finally, if you want to figure out the average value or the mean, you can just call rmean. And there we have the average was 60.8, so it calculates the mean. Something else you can do is you can reshape arrays. This is sometimes useful. So if I check out the shape parameter, notice how I'm just calling shape with no parentheses here. It returns back a shape, 10, comma, and then nothing, because it's actually just a single vector. What I could do is say reshape this to another set of dimensions. So if I do Shift Tab here, it'll say, okay, what shape do you want it in now? Well, let's imagine that I wanted to reshape it to be 2 by 5. So now it's reshaped this to be 2 rows by 5 columns. If I try to choose values that don't make sense, such as 2 by 10, it's going to give you an error. It's going to say, hey, I can't reshape an array size 10 into shape 2 by 10, which makes sense because if you have an array of 2 by 10, that means there's 2 times 10 elements. That means 20 elements. However, you only had 10 elements to work with. So that's why it's giving us an error here, because those dimensions don't make sense. But we could always reshape to something that does make sense. It's like 5 by 2. Since 5 times 2 is 10, and we have 10 elements, that works out just fine. Okay, so that's the basics of operations that we need to know. Lastly, we want to understand indexing. So I'm going to make a couple more cells here to clear out some of the space. And I'm going to create a variable called mat for matrix. We'll say np.arrange. 0 to 100, and then immediately after this, instead of doing this in 2 steps, I'm going to do it all in 1 step. I'm going to reshape this to 10 by 10. And now if I check out my mat, I have this array of all the numbers from 0 stopped until 100 or 99. And then if I want to check the shape of this, it's 10 by 10. So let's imagine that I wanted to grab a single digit from this array. What I do is I use indexing. So let's say I want the value at row at index 0, where column is index 1. So what value is that? Well, row 0 is this first row. Column 1 is the second column, because if we start counting at index 0, 1, so that's going to hopefully return back 1. And the notation for this, or syntax for this, is MAT, or whatever your matrix or array happens to be called, and then you pass in the row, comma, the column. Run that, and we get back that value of 1. I would encourage you now to pause the video and try to choose a number somewhere in this matrix, and then see if you can index out that number. So for example, see if you can grab just the number 46 from this matrix based off the logic we showed you here. Okay, so let's quickly show you how to do that. So if I wanted 46, then that's at 0, 1, 2, 3, 4. So that's row number 4, and it's at column 6. So here we just actually wrote out row and column, but you can pass in the numbers directly. And there's 46. So that's also kind of the reason we chose these particular values from 0 to 99, because you can really quite clearly see the index locations. Notice how the first number here is representative of the index of that actual row, and the number here is representative of the index of that column. So 46 was actually quite easy. It was 4,6. Now let's imagine you wanted to grab all the items in a row, or all the items in a column. You do that with slicing. So we say mat, and then we're going to say colon, and then pass in some column value. Let's go ahead and pass in column 1. So what that returns back is every single value for every single row in the column 1. So if I take a look at my matrix again, notice here that my matrix has this column 1, 11, 21. So that's the column I asked for. And with the colon, you ask for everything. So in this dimension, those were the rows. So I asked for the value of every single row just for that particular column. So it's essentially just asking for that entire column back. You'll notice here that the shape returned is 10 comma nothing. If you actually wanted to get it in this shape, then you would have to say mat colon comma 1, and then reshape to the particular shape you wanted. So if you wanted it to be 1 row by 10 columns, you could get something like this, or you could reverse it to have it this other way. That looks more like the original. Keep in mind, depending on what IDE you're running, you may not actually see this output formatted the same way, but hopefully you kind of get the idea here of the different shapes something can be returned in. Okay, so that returns back an entire column. If you want it back an entire row, it's essentially the opposite. You ask for every column for a particular row. So let's get a row here. Let's just row 2. And then we'll say colon, give me everything there. And now we get back everything in that row. So notice when I ask for the array, I'm basically saying, okay, go 0, 1, 2, and then give me every single column for this row, which is just that row itself, 20, 21, 22, and so on. Finally, often you can actually grab just mere chunks of this. So the way we do that is through slicing. And then we use slice notation just like you do for a normal Python list. So let's imagine I wanted to grab this first 3 by 3 here. What I could do is say starting at index 0, colon 3 for those rows, and then for the columns, do the same thing, 0, colon 3. And what that does is it says, okay, grab all the rows starting at 0 up to, not including 3. So here are all the rows, 0, 1, and 2. And then grab all those columns, 0, and then 1, and then 2. So we can expand this to get a better idea. So if I kept going with those particular columns, it'd start giving me more of those rows. So give me the additional column there, 0, 1, 2, and 3. Essentially, this is just normal Python slicing notation, just the same way you would slice a normal Python string or a normal Python list, but now it's happening along 2 dimensions. Don't worry too much if this notation is a little confusing to you. We actually won't really see it that often throughout the course. Usually what we end up doing is we just take a quick slice of maybe everything, and then reassign it. So the last thing I want to show you is if you wanted to actually reassign these numbers to a different value, you could say equals 0. And then if we check out the matrix again, the original matrix has now been affected, and now that entire chunk is equal to 0. If you want to actually affect a kind of copy of the matrix, what you could do is say my new mat, or whatever you happen to call this variable, and then say mat, and then call copy. And that's a command we'll see throughout the course. So sometimes you want to make a copy and then maybe set all the values to something else. So if I wanted to reset all the values, so if I look at my new mat right here, is a copy of that matrix that's already been affected. Let's actually just turn everything on this top half into zeros. So how do I do that? Well, I want to grab everything from, let's say, 0 up to, but not including 6. So I want to grab all those rows, and then I want to grab all the columns. So I'm actually just going to grab everything there. And let's set those all to 0. In fact, let's set them all to 99, just so it's really obvious. We'll do 999. There we go. And if I check out my new mat, now we go ahead and set kind of that first top half into 999. Okay, again, really just doing normal Python slicing notation that you've seen before if you're already experienced with Python lists and strings, just doing it along 2 dimensions. And as I mentioned, we really don't do this that often throughout the course. It's just a few times we want to reassign some image pixels. Okay, so that's the basics of NumPy. Coming up next, we're going to learn about NumPy. Well, we'll actually learn first what an image actually is in reference to a computer, and then we'll learn how to directly work with NumPy and images. Thanks, and I'll see you there. Welcome back. Now that we understand how to work with the basics of NumPy arrays, let's quickly talk about what an image actually is. So before we talk about how to use NumPy specifically with image files, let's first discuss how computers themselves handle images. Let's imagine that we wanted to build software that could sort out mail based on the zip code of the address written on the envelope. Often mail is handwritten, which means we would somehow need to begin to understand how to use computer vision to actually read in image data of these handwritten digits. So most likely we're going to be working with an image such as a photograph of the envelope, like a PNG or JPEG, and we want to understand how does a computer actually represent image data. Let's imagine we have a simple image of a handwritten number. So here we have images of the numbers 1, 2, and 3, and these are either JPEG or PNG files. Each single digit image can be actually represented as an array. So here we have the numbers 0 through 9, and these are all being represented as an array. So for example, here is a number represented by 28 by 28 pixels. You can imagine that as we get more and more pixels, we'll have finer and finer resolution. You'll also notice that the image on the left is grayscale, meaning it's only black or white or some color of gray, and it's being represented as an array with values ranging from 0 to 1. So how dark a pixel should be can be represented as those values between 0 and 1. So you'll notice here we have a number 1 as the handwritten digit, and where it's darkest, it's represented as a single digit 1, and where it's completely white, it's represented as 0. Now, often default images, when you actually read them in, they have values between 0 and 255, where 255 is the highest or brightest value, and 0 is the darkest. The range 0 to 255, that actually has to do with how computers store 8-bit numbers. That's a bit outside the scope of this course, and we really don't need to understand it, but at the end, I'll show you a couple links that you can check out for more information. Now, if you ever wanted to get those values between 0 and 255 to be between 0 and 1, all you would need to do is divide by the max value, 255, in order to normalize to between 0 and 1. And later on in the course, we'll see some examples of doing that. So we've understood how grayscale images can be represented as arrays, but what about color images? Color images can be represented as a combination of red, green, and blue. Additive color mixing allows us to represent a wide variety of colors by simply combining different amounts of RGB, or red, green, blue. And RGB allows us to produce a range of colors. And here we can see the entire dynamic range that just red, green, and blue allows you to create. This sort of image is known as a color triangle, and basically what that means is only colors within this triangle can be reproduced by mixing the primary colors, that is red, green, and blue. Colors outside the color triangle are therefore shown here as gray. And the primaries and the D65, that point in the middle, that's the white point, and basically shows you the edges of what's producible. And keep in mind that humans themselves have limits as far as what colors they can see. But obviously red, green, and blue allows for quite a wide range. Later on in the course, we're going to be learning about alternative color mappings that can be applied to images that go beyond just red, green, and blue. But for now, red, green, and blue will be more than enough for us. So each color channel will have intensity values. And you may have already seen this sort of representation in other software with RGB sliders. In fact, you can just Google RGB slider to play around with these sort of values. So here you can play around with the values of red, green, and blue to produce different colors, all the way values from 0 to 255. So what does that actually mean when you read in a color image with Python and a computer in general? So what happens is when you read in an image, it's going to actually have 3 dimensions, a height dimension, a width dimension, and then 3 dimensions for these color channels, red, green, and blue. So this means that you're reading in the image, and if you were to check its shape, if you read it in as a NumPy array, the shape is going to be something like 1280 by 720 by 3. So that would be the pixel width, the pixel height, and then the actual 3 color channels. So if we were to actually visualize this, basically you have a 3-dimensional array where we have the typical 2 dimensions, except now you have 3 of those, 1 for each major color. Keep in mind the computer itself won't know that a channel is red. It just knows that there are now 3 intensity channels, essentially 3 sort of grayscale channels representing a color. So notice that when the computer actually reads it in, it gets something that looks like this last column here, black and white. It's up to whatever software you're using to actually represent those as color in order to combine them to get that left image all the way on the left where we have the parrot. So keep in mind, we're still getting values between 0 and 255. It's just now we have 3 of those mappings, 1 for red, 1 for green, and 1 for blue. So the user needs to dictate which channel is for which color. Each channel alone is essentially the same as a single grayscale image. So let's explore this further with NumPy and Python. I also highly encourage you to check out the Wikipedia article on RGB color channeling. It's called RGB Color Model, and it has a lot of interesting details as well as the history of RGB color model and a couple of more fun things to play around with. Okay, so let's move on and explore this further with NumPy and Python. I'll see you at the next lecture. Welcome back, everyone. In this lecture, we're going to talk about images and NumPy. NumPy by itself can't actually directly open a .jpeg or .png extension file. Instead, we need to use it in conjunction with what's known as the PILO or PIL library, which stands for Python Imaging Library. Let's go ahead and open up a notebook and take a look at how this all works. Alright, so to begin, we're going to start by importing NumPy as np, and then we'll also say import matplotlib.pyplot as plt. Matplotlib is a library that's actually going to allow us to plot out and display images inside of the notebook. Now, in order to display things inside of the notebook, we also need to write out %, matplotlib inline. Then go ahead and run that. Keep in mind, as a quick note, the actual latest versions of Jupyter and Jupyter Lab don't require this matplotlib inline, but I'm leaving it here just in case because it doesn't do any harm. And sometimes there's bugs if you don't have that actual line. So that allows us to display plots inline in the actual notebook. Now it's time to actually try to open up an image with NumPy. Now in order to do that, we first need to open it using the Python imaging library. So we'll say from PIL in all caps, import image. And notice I is capitalized there. So this is an image function that allows us to open up images, and actually then we're going to be able to transform this image into an array that NumPy can understand. So I will say pic is equal to image.open, and then you can just provide the file path for any image. Now, if you downloaded the course notes, you'll notice that there's a data folder here, and there's a file called 00-puppy.jpg in the data folder of our actual notes. So that's what I'm going to provide the file path there. So I will say data 00-puppy.jpg. You need to make sure that you actually are providing the right path. So in my case, this data folder is actually in the same location as this notebook, but if you're one location deeper, you may need to say .. / So it really all depends on where this notebook's actually located in conjunction to your actual JPEG file that you're trying to open. If you are unsure, just go ahead and pass in the whole file path, which is going to be something like C, users, then your username, and so on. So just keep that in mind, otherwise you'll get an error. So I'm going to now collapse this. So looks like I got the error right now. I'm going to undo that /. There we go. So now I'm ready to go. And if I just take a look at this pic and do Shift Enter, I get back this pic of this adorable puppy. Now let's go ahead and take a look at what type of object this is. So if I were to say type pic, it's a right now Python imaging library, or PIL, JPEG image plugin. It's a JPEG image file. So right now it's a JPEG, which means that NumPy can't actually deal with it. But what we can do is transform it into an array. So we're going to say pic_arr is equal to np.asArray, and then pass in that pic. And now if I take a look at the type of pic array, it's now a NumPy array. And in fact, let's take a look at its shape. So its shape right now is 1300 by 1950 pixels with 3 color channels. And if I say plt.imshow, which is going to allow us to show this array as an image, I'll pass in pic array, run that, and then I get to see the actual array laid out. So here's the image, and this plt.imshow, it's kind of a special function that's specially designed to show images that are transformed to as arrays. Now notice that we get these grids. So I can see here how it's 1300 pixels in length and about 1950 in width. And there's 3 channels here, the red, the green, and the blue. So let's actually access one of these channels by itself so we can see what's going on here. So I'm going to say pic red is equal to pic ARR, and I'm going to make a copy of it. So previously in the NumPy lecture, we showed you how we can make copies. Now if I actually just display this red image, I get back right now the same image as I did before, which makes sense because it was just a copy. However, let's try the following. We're going to try to zero out the contribution from the green and the blue channels. So what we're going to do is, if we're going to take a look at this array, it's 3 channels right now. One 1300 by 1950 array for red, one 1300 by 1950 for blue, and another one for green. In our case, it's going to be RGB, or red, green, blue. So how do we actually zero out these values? Well, what I'm going to do is say pic red, and remember the shape of this is 1300 by 1950, essentially 3 arrays of 1300 by 1950. I'm going to say pic red, and then I'm going to grab all the rows and all the columns in the green channel. So the way this is formatted is it goes red channel, then green channel, and then blue channel. So each of these shapes, one stands for red, one stands for green, and one stands for blue. So if I take a look at just this, which means everything in that 1300, everything in 1950, but just one, that actually stands for the green channel, because R would be 0. So let's go ahead and display this. We'll say plt.imshow, and you'll notice something funny happen here. You'll notice now the coloring seems very strange, and that's because if we take a look at these values, they're now all between 0 and 255, and Matplotlib by default will show this using what's known as a Viridis color scale. So when we ran imshow on this, So if I say plt.imshow, it took those values and applied some sort of color scale. And the default, like I said, is this. If you actually check out the matplotlib documentation on their color codes, they have perceptually uniform sequential color mappings, and this is this one that goes from purple all the way to yellow. And it's actually specially designed for people who are colorblind, and these are all actually designed for people that are colorblind. However, this actually isn't really an accurate representation of what this particular array represents. In fact, what's probably more accurate is if we were to say cmap gray and then run this. This stands for color mapping, and we choose gray, which essentially just says show this in grayscale. So this right now that we're showing right here, this is the red channel values. They're all between 0 and 255. Remember, there's two more of these, one for green and one for blue. So let's check it out. This is the one for green. And then let's check out the one for blue. You'll notice that they're all a little slightly different. So for example, if we take a closer look at the red channel, remember 255, that means a full pure red. 0 will then mean no red, pure black. So that means when we're actually viewing this in grayscale, the closer to white, that means more red for this particular image. So if we take a look at the ears here, they tend to be pretty white, which means there's high values of red there. And if we were to scroll back and take a look at the actual dog's ears, you'll notice that his ears actually do contain quite a bit of red. It's kind of an orange color. But if we take a look at the other colors, such as the color mapping for green or the color mapping for blue, you'll notice his ears appear now quite dark. That means there's not a whole lot of green in his ears. There's a little bit, but there's definitely not a whole lot of blue. So again, here we're displaying the three different channels as grayscale. So this is red because it's the first one we indexed at 0. This is green, the second one we indexed at 1. And this is blue, we indexed at 2. So again, take a look back at the slides of what is an image to better understand what these three images are actually showing you, because it's kind of hard to understand without the full context of the what is an image lecture. Okay, now back to the task at hand. Let's imagine that I actually made all these values 0, which means I said the following. I'm going to grab my pick red, and I'm going to set everything in the green channel. If we just take a look at this, we have all these values from 0 to 255. I'm going to set these all equal to 0. I'm going to zero them out. So now I've completely gotten rid of the green channel. So let's see what our picture now looks like. We'll say plt imshow pick red, and you'll now notice that it looks a lot stranger. In fact, it looks a lot more purplish, and that's because the only two colors that are left are blue and red, which together make purple. So now we're basically seeing everything without the color green. Now let's take this a step further and remove the contribution from blue. So what we're going to do here again is say pick red, and I'm going to grab all the pixels, except now I'm going to grab them in the index 2 channel, which is the blue channel, because it goes red, green, blue, and we're going to set that to 0. And now when I see pick red again, I've completely gotten rid of blue. Essentially now there's then no more purple, and we're seeing the red channel completely. Something to keep in mind is this pick red, its shape is still 3 channels across. So a lot of times students are a bit confused as to what's the difference between pick red here versus the pick red that we were seeing earlier when we actually just grabbed 1. And that's because we're seeing all 3 channels at once instead of just one channel. So if I were to take the look shape of this guy, this is just 1300 by 1950. So this is just one single channel. And if I do the same for the other ones, you'll notice the shape doesn't change. When I say pick red without any indexing, it still has information for all 3 channels, except cleverly, we went ahead and zeroed out the green channel as well as the blue channel, which is why this picture only shows up with the red. Okay, so I know that was a bit complicated because of the NumPy indexing involved, but the actual idea is quite simple. Essentially, we know the image has 3 channels, a red one, a green one, and a blue one. We changed all the values in the green channel and the blue channel, those 2 layers, we made them all 0, which means we basically told the image, hey, there's no longer any contribution from green and also no longer any contribution from blue. So then when the image or PLT was asked, hey, can you show me what this adjusted image looks like? It could only show what was in the existing red channel, which is why everything's now colored red. That's different than what we did before, which was color mapping a single channel to grayscale. Okay, if you have any questions, feel free to post the Q&A forums, but definitely do another watching of the what is an image to further understand what's going on here. Thanks, and we'll see you at the next lecture.